In the world of tomorrow, plastics will certainly call the tune. The ingenious alchemy of coal and oil provides the material. Ingenious machinery presses and stamps and molds the material into a wide variety of products, articles for household use, as well as tools for industry.
The future will bring plastic fabrics wondrously fine, yet resistant to wear, wrinkles, and stains. There will be furniture combining strength with lightness, comfort with eye appeal, with many contributions of the kingdom of plastics designed for practical, gracious living.
The new streamlined plastics present a colorful array. The great range of hues and shades in plastic products presents a challenge for reproduction that is easily met.
So in the years ahead, dreams like this and many more will become realities.
Plastics are everywhere. We use them in all kinds of things. We can't imagine a world without plastic. The problem is when we use a bottle like this, we just throw it away and it ends up somewhere like here. When we make plastic, we're using a really valuable resource, oil. When we throw plastic away, we're using another resource, land. But plastic's a really useful material. So what is the future for plastic?
Plastic is just one of a vast range of products derived from oil. Crude oil is a mixture of liquids and gases. These are mainly hydrocarbons, molecules containing only hydrogen and carbon. Much of the oil extracted from the North Sea is transferred by pipeline to Grangemouth, where it's refined on a massive scale. Fractional distillation separates out the useful components. Hot crude oil is fed in at the base of a tall column, which is kept hotter at the bottom than at the top. Fractions like diesel oils, which contain heavy hydrocarbons, tend to stay near the bottom of the tower. Lighter hydrocarbons have lower boiling points, so they vaporize and rise up the tower, where they cool and eventually recondense. The naphtha fraction, which is used for making plastic, is extracted near the top. The naphtha fraction contains a family of hydrocarbons called alkanes.
A mixture of alkanes from the refinery is fed into the furnaces behind me. In there, it is heated to very high temperatures, which cause the molecules to break into smaller molecules known as alkenes. This process is known as cracking.
The carbon atoms in alkanes are linked by single chemical bonds. Cracking produces alkenes, which contain a double bond.
This is ethene. It has two carbon atoms attached by a double bond. Each of the carbon atoms has two hydrogens attached. The double bond allows us to join lots of these molecules together to make polyethene or polythene.
Polythene is produced from ethene by polymerization. Ethene is a gas, and a strong vessel is needed to contain it, since the process takes place at very high temperature and pressure. Even under these conditions, polymerization won't go by itself, so a catalyst has to be added. Large amounts of ethene gas are pumped in along a pipe to create a high pressure. The more ethene molecules there are to collide with each other, the faster the polymerization will happen. Once their double bonds are broken, the ethene molecules can link together using single bonds, and ethene gas becomes solid polythene. one of the most widely used polymers.
Polymers are made of very long chain molecules. I've got a model here of polythene. The black beads represent the carbon atoms and the white beads represent the hydrogen atoms. A typical molecule would have many thousands of these carbon atoms all joined together, and on this scale it would be a few kilometres long. The bonds between the carbon atoms are covalent bonds, which are very strong, but it's possible to rotate the molecule around these covalent bonds, and this makes these long chain molecules very flexible indeed. These beads are a much better model of what a polymer chain is like when it's warm and flexible. And we can mould it into whatever shape we like. To keep it in that shape, we cool it down. And this does two things to the molecules. Firstly, it can stop them rotating around the covalent bonds, and this locks the polymer chain in shape, therefore it can't move. The second thing it can do is, as we cool it down, the polymer chains pack together very closely, and they don't have room to move. Therefore, again, they're locked in shape. If we heat this polymer up again, it will become flexible again. And polymers that can be processed like this are called thermoplastic. There are many different thermoplastics with different properties, but they can all be moulded in this way, and that's what makes them so useful and so widespread.
This is polythene, our basic raw material. When we heat this, it becomes soft and mouldable. From these little beads we can make any shape we want. Today this machine is set up to make wheel bins. We take the heated polythene, heat it up to 240 degrees Celsius and push that into the mould. Once the mould is full, we need to cool it down to below 80 degrees C. That then retains the shape. That's the wheel bin made. The process is cost effective and simple. If we wish to make another shape, we simply change the mould and set up, and we have another product. This may look like a reject, but in fact we've used air to blow it from the mould, it's deformed the base. One of the properties of plastic is that it has a memory, and by simply tapping it, it returns to the shape it picked up within the mould.
Once I used plastic for the first time, I actually found it so versatile and just really exciting. It gave me lots of colours and textures and surfaces, and because it's a relatively new material, it's still got possibilities for experimenting. I'm starting to heat up a piece of acrylic rod, and you can see that it's becoming flexible. The heat changes the chemical structure so that you can actually start playing with the material. Using various pliers and tweezers and bits and pieces, you can start to shape and structure the perspex. You can see it starts to really become quite jelly-like. And then I can stretch it and bend it, start to form it. Once I've held the piece of perspex into the shape that I want, I'll quench it in some water to actually make it a rigid form. And once I've got the form and the shape to the way that I want it, I'll then cut the component off, and I end up with a piece like this, which I then will colour and mask off different areas to get different colours to make some brooches. in lots of different colours, but some of the interesting things that happen are if you put methylated spirits on it, it brings out lots of fractures, and also you can press it into different textured surfaces so that it picks up sort of nice textures and different patterns.
Any thermoplastic can be remoulded into a new shape. Thermosets, such as polyester resin, can only be moulded once.
I also make other jewellery pieces like these using a polyester resin which is poured into a silicone rubber mould, like so. Once the resin's set and I take it out of the mould, I cut the excess off and I file it and sand it so that I get a nice smooth shape. And once I've done that, I use a thicker polyester resin and texture the surface like this, and then I assemble it with silver components to make earrings. Because this is a thermoset plastic, I can't actually reshape it once it's set, but I can, because it's so versatile, use it lots of different ways. I can make larger objects with different textures, colours. It's wonderful for jewellery, it's excellent.
In a thermoset, the polymer molecules become bonded to each other to form a network that is not flexible. If we reheat a thermoset, these bonds won't break, so we cannot remould a thermoset, unlike a thermoplastic.
The properties of all plastics depend on the way they're processed. Because of its lightweight strength, polythene is used to make shopping bags and thousands of other durable items. Of course, even a solid block of polythene has its limitations. But polythene can be given unusual properties if you process it in the right way.
As I start pulling on this piece of polythene, it's easy to stretch. This is because I'm uncoiling the long chain molecules. But as I stretch it more and more, these molecules are lining up, and I reach a point where it's hard to stretch anymore. The polymer is now much stronger. Let me use these beads to show you what's happening. As we stretch out the polymer, the molecules line up. We reach a point where all the molecules are lined up. To stretch it any further would require breaking the strong covalent bonds. Polymers with the molecules lined up like this will be very strong.
This target was made from stretched polythene fibres. The target can absorb a heavy impact without breaking, but it's made from exactly the same polymer as cling film.
One of the great things about plastic is its strength and its durability, but that can also present us with some problems. If we throw plastics away to a landfill site like this, they won't rot and they'll be here for years and years to come. So what can we do with plastic? We could reduce the amount that we use. We could choose things with less packaging. Or we could reuse plastic, like by refilling bottles. We could burn plastics, but that could release harmful gases. And also once we've burnt it, the plastic's lost forever. So one of the best and most practical options for plastic at the moment is to recycle it.
Here at the factory, we recycle everything we can. We recycle our plastic waste and products at the end of their life. Things such as crates, old dustbins, polythene bottles. And this is how it ends up. This we can take and reprocess, reheat and form into anything we want. Here behind me is some of the many tons of recycled plastic that we go through here at Rotherham. Recycling in this way has got to be a major part of the future for plastics. Here we're testing our wheel bins. We fill them with 100 kilos of polythene granules and we drop them from 4 metres. Obviously we're looking for the bins not to split and still to be functional. Okay? Here's where the bins hit the floor. As you can see, it's slightly deformed. But over the next 2 or 3 days it will recover, leaving only some slight stress marks. But the bin is totally functional. We also make wheel bins out of recycled material. We test them in exactly the same way and they perform just as well.
Before plastics can be recycled, they need to be sorted according to which polymer they're made of. They'll be sorted into PE, polyethylene, PVC, which is polyvinyl chloride, and PET, which is polyester. At the moment, sorting the plastics is done by hand and it takes a lot of time and effort. In the future, with new technologies and maybe electronic labelling, this will be a lot simpler. But whatever happens, recycling is well worth the effort. Just 5 of these bottles can be made into this fibre and fill a jacket like the one I'm wearing.
Mechanical recycling is now widely practiced, but it is limited because you can only recycle polythene to make more polythene, PVC to make more PVC, and so on. For true recycling, we need to go back to an earlier stage of the original manufacture process.
In this pilot plant, we take a variety of waste plastics and turn them into a material which resembles the naphtha fraction of crude oil. The plastic enters the reactor where it's heated to a high temperature in the absence of oxygen. This reverses the polymerization reaction by breaking the long molecules into lots of shorter chains. What we get from the process is this. Now this can be used in our cracking furnaces to produce alkenes. These alkenes can then be polymerized. So from our waste plastics we can get any polymer we want.
If this plastic hadn't been collected and sorted, it would all have ended up in landfill. It'd be buried underground, a complete waste. The thing is, we can recycle it.
The mechanical recycling of plastics has its limitations. So the future for plastics must include the ability to recycle to a raw material which will enable you to make any product you want.
In the last 50 years, we've all become used to using polymers in our everyday lives. But polymers can be used for many other things. We could have polymers that can be used in our bodies for artificial bone and artificial organs. We could have polymers that conduct electricity and can be used in electronic components and in batteries. We could have polymers that can withstand very high temperatures and be used in car engines. In fact, polymers can be designed to almost any purpose, and we're going to be using them much more in the future.
In the future, we're going to have to take more care of how we use plastic. The more we understand about its properties, the easier it is for us to use it more effectively and not misuse it.